This is parabolic motion. Now, we started last week, and I gave kind of the first preliminary equations, but that was just basically kind of a demonstration. We got a initial, basically a introduction of two-dimensional motion, of parabolic motion, and two-dimensional in general. Parabolic being a specific case of two-dimensional, but we really want to, right now, we want to derive the equation specifically for parabolic motion. And there are 7 equations. 7 equations plus some geometric contributions to those equations. I wrote down the first 5, but it wasn't even really all of the implications of the first 5. So that's, now the example that class demonstration, I think last week I had was, an object falling and then an object, free fall motion with parabolic motion. And I think we came to the realization that, when I dropped the quarter and flicked one quarter off the ledge, even though one of the quarters translated and hit some distance x away from the vertical distance associated with the ledge, while the other just dropped straight down, they both hit the ground at the same time. So when we have talked about the one that was parabolic, we assumed that there was no air resistance, no drag associated with air. And what I told you is that once I give it a horizontal thrust with my finger, there is a force while it's in contact with my finger, but we enter the problem essentially after it leaves my finger and even after it leaves the ledge. And once it leaves the ledge, if we're not assuming drag, if we're excluding drag, then there is no force in the x direction to change the motion. The only force it experiences is in the vertical, and just like the object that we dropped, the free fall object, gravity is causing it to accelerate down. So if you were to look at just the motion in the y direction, that motion is basically free fall. It's just like the motion of the object that is, for the parabolic object, it's just like the object that's free falling. So the general equations that apply to the object that is experiencing parabolic motion in the y direction, again, right? Clearly, from sound and everything, it looks like it's hitting about the same time, excluding human error. So in the y direction, if I were to break up the motion of the parabolic object in x and y, in the y direction, its y motion is just doing this, just like the one that I dropped. In the x motion, because it has a velocity in the x direction, and once it leaves the ledge, there is nothing like drag or air or another force coming on in the x direction to slow it down. And again, this really is, we need to investigate Newton's laws to fully understand this, but at least your intuition, you should be able to understand that if there is nothing retarding the motion or helping the motion in the x direction, whatever motion it has, it's just going to maintain that motion, right? So in the x direction, we basically have the object moving along at a constant velocity. So when you combine free fall in the y direction and constant motion in the x direction, what you get is that. So literally, the motion of the object in the 2 different directions are really different, caused by different external phenomena. And when we combine them, the combined motion basically causes it to look like a parabola. So that's as far as we had gotten with that class demonstration. Okay. Now, I want to switch perspectives to continue talking about parabolic motion. And it's just not a very drastic difference in perspective, but slightly different, but still something you're familiar with. And this is the perspective. If we were in class, I've got a couple of, footballs, like those Nerf balls or something. I'll throw them out to you in class. So this is a situation where we take a ball and I would throw it to a couple of you, throw it back to me. Right? And we're seeing, again, demonstrating the first part of the technique, problem solving technique. When we look at this is a different type of parabola than the one that we showed with the object falling. But still, it's a parabola, right? Now, there's some qualitative things in one-dimensional motion I didn't really get into. I think I'm going to have to try to post that. I don't think I went into full detail on all that, but one of the things that we can understand when we're looking at the path of an object moving is that everywhere along that path, the velocity of the object is tangent to the path. That kind of makes sense, right? If you're in a car and you're going around a curve, you start to slide. It's almost like if you mapped out a path of the motion, or maybe that's not the best example. The best example, I guess, would be if I'm twirling an object. A better example. If I'm twirling an object, like this guy, in a circle, right? If at some point I snip the string, so it's mapping out a circle. At some point, if I snip the string, at the point where that string snips, the thing just moves straight along that path, tangent to the point of the circle where it was. Right? So if for a physical path that something has, if something is moving along a physical path, at any end, the path is a curved path. At any point along that path, the direction of the velocity is a tangent to that path. So with that in mind, I want to look at the kind of parabola that occurs. I call it the perfect parabola if you're on a flat surface. When you're throwing like a football on a gridiron, or you're hitting a golf ball, on a flat golf course, or any number of situations where you have balls being thrown, a basketball. Now, in those cases, it's not technically perfect. Perfect meaning that perfect parabola is one where the final y position is the same as the initial position. So we're going to make that assumption. Vincent, you got a question? No. So we're going to assume that. Maybe think of this as a football being thrown down a football field. However, technically speaking, it's not quite a perfect parabola because the y position at which the object is being thrown is not on the ground. We're going to exaggerate that just like we do with frictionless surfaces and things. We're going to assume that for our ball being thrown, it actually starts literally on the ground. Now, we change that around once we understand, have the equations developed, and not all the problems are going to do that. I'm just doing it now just for the purpose of illustration to more easily present these equations of motion for parabolic motion. So we're going to assume that we have a ball and it's being projected, a ball or projectile from the ground, and it's going to follow a path like this. Oh. Now I'm going to put my coordinate axis so that the x-axis is on the ground. So we're going to assume that x is the ground and y is the vertical. Okay, so yeah, I got the ground there. Yeah, supposed to be a flower. Now we're throwing something, it's going to follow a parabolic path like the ones I've just illustrated. And maybe that looks something like this. Now, as I said, this is the physical path that the ball is taking. At any point that I am on this path, the velocity of the ball is tangent to that path. Let's look at a specific case at the origin where the ball starts. If I were to draw a vector that represents the velocity, the initial velocity, which I'm going to call V naught, then that thing would look something like this. Now, the magnitude, yeah, it's going to technically, when you draw vectors, the magnitude was supposed to somehow represent the length of the vector represents the magnitude, but it's arbitrary. But still, that I'm going to call V naught, the initial velocity. Okay, and it's making an angle theta naught, the initial angle, relative to the well, in this case, is measured relative to the x-axis, theta naught. Now, I can yeah, and so at every point, we'll see that, right? We'll see that when the velocity gets here, it's going to be tangent, but at a slightly different angle because the angle is changing relative to the vertical, right? And whatever the velocity is at that point, it shouldn't quite be as large as this vector because it's at least one component, the y component is decreasing, as we'll reiterate momentarily. But I don't know, maybe it looks like maybe it looks like I think somebody's mic is on. It might be you, Vincent. Yeah, thank you. Maybe it's not going to be as big, so maybe it looks something like, or as long, that is to say. Maybe it looks something like that. But we'll get to that momentarily. Let's focus on just the initial here before we take our break. 15 minutes. Let me blow this up a little bit, just the initial point there. If I blow it up, first of all, look, I can drop a perpendicular. I can consider the components of V naught. And I defined to you what a component was last week. Remember, it's the projection from a higher dimension to a lower dimension. So here, whereas V naught is a two-dimensional vector in the two-dimensional space, y and x, when I find this component, I'm projecting down, basically V x naught is the projection of V naught onto the x-axis. And similarly, V y naught is the projection of V naught onto the y-axis. But from that, I can construct a right triangle. I'm going to blow it up so we can play with it down here. This guy is V naught. This guy is Vx naught. And this guy is Vy naught. And the angle theta naught is here. So using my trigonometric relationships, I can write V naught in terms of, or V x naught and Vy naught in terms of the initial velocity V naught and the initial angle, theta naught. Now, for the purposes of clarity, whenever I list the equations, so I separate out the geometry and math stuff from the physics, just in my mind, just the way I organize it. So here, I'm going to write out a series of equations that just define the geometry of the relationship as illustrated by this right triangle. And we see that Vx naught is equal to V naught times the cosine of theta naught. Vy naught is equal to V naught times the sine of theta naught. And of course, we have the Pythagorean theorem. V naught squared is equal to Vy naught squared plus V x naught squared. And also the tangent equation. Tangent of theta naught is equal to the magnitude of Vy naught divided by V x naught. Okay? Any questions about that? Now, let's go to this point here. Clearly, you can see that if the velocity, well, maybe it's not clear, but I'm going to make it clear. If the velocity is tangent to the path, then all you need to do to verify that the direction is changing is to just take a straight edge and put it tangent to the path at one point, and then follow that straight edge around as you move along the path. You can see that the tangent direction is changing. Up here, for example, it's completely horizontal, and the velocity is pointing directly along the x-axis. So that shows you that the angle that the ball is making, the velocity vector of the ball, is changing as it moves along its parabolic path. And we will show that the magnitude, the total magnitude, is also changing. Now, if I were to look at this point, I could also construct a right triangle from that point, that even though theta naught and V naught is changing, and Vy naught actually as well, what we will see is that the relationship between the total velocity and the components of the velocity maintain this same kind of trigonometric relationship. That is to say, here, I'm not going to call this V naught, I'm going to call it V, because the velocity is decreasing as the object is changing, as it moves up. We'll talk about why here in a second, but it still is going to have an x component, Vx and Vy. I'm not going to call it Vx naught and Vy naught because that's reserved for the initial value of these quantities along this trajectory. However, even though it's some other arbitrary velocity, it's still going to have x component and y components. And those components will still be defined by these kinds of relationships. So in fact, anywhere along the parabolic path, these trigonometric relationships are true, such that I can say that, I'm going to write them as different equations, such that I can say that Vx is equal to V times the cosine of theta, whatever that angle. And again, that angle is not the same angle, it's a different angle. I'll call it just theta, as opposed to, if you can see that, as opposed to theta naught. Yeah, let's see that very well with different color. I'm just going to put an angle representation like that. Nothing wrong. It's so hard to see it. We'll put this back in. Arrow, arrow. Put that in. And reinforce the parallel. Okay. Vy is equal to V times the sine of theta. Let me come over and make it. V is equal to V times the cosine of theta. V, so this is Vx. So Vx equals V times sine, and Vy equals V times the sine of theta. And so on and so forth, right? V squared is equal to Vy squared plus Vx squared. And obviously then another way to write this, right? Tan theta is equal to Vy over Vx, or theta is equal to the inverse tangent of Vy, absolute value of Vy over Vx. So those are the trigonometric relationships between those quantities. Now, the criteria for this kind of motion, I want to put it up here, is that in the x direction, there is no acceleration, assuming that we don't consider drag force. So ax equals 0 for parabolic motion. In the y direction, the only force on the object is the force of gravity, and we know that implies free fall motion. And for anything experiencing free fall motion, the acceleration is negative g. So the criteria for this motion is that ay equals negative g and ax equals 0. Okay? And sometimes I put Roman numeral for these guys. I'll do letters or something. So. I'm going to do this 1A, 2A, 3A, 4A, and this will be 1B, 2B, 3B, 4B. I just want to separate out these equations from the physics. And then presenting this, the physics equations. Okay. What I want to ask is, or point out, so I told you that this velocity is changing as it moves along the path. And I told you that once I give it a velocity, I flick it off the curve, in the x direction, it doesn't change its velocity because there's nothing to accelerate or decelerate. In the y direction, it definitely changes its velocity because there is something to accelerate or decelerate. What is that? The force of gravity. And so the acceleration is negative g. And it doesn't matter whether it's going up or going down, whether I'm talking about the ball being flicked off the ledge or whether I'm throwing a football or a baseball, right? Once I give it that component of velocity, the x component is not going to change. Why? Because if I'm not considering drag force, there's nothing in the horizontal direction to change the motion. So since ax is negative, ax equals 0, I can add to this criteria that, one of the caveats of that is that Vx naught equals Vx at any other point in the path, meaning Vx doesn't change. I'm not emphasizing time dependence, but here I could probably do that. I could say that the initial velocity is equal to the velocity in the x direction. The initial velocity in the x direction is equal to the velocity of the x direction at any other time. which means that it doesn't change. Not the case for the y direction. The velocity in the y direction is changing. It's just, it certainly has a v initial velocity, but, at some other time, the y velocity will not necessarily be the same. So as a complete set of criteria for parabolic motion, these statements, mathematical statements here, are what I write. So this is kind of the pictorial introduction of parabolic motion. We're going to complete this little curve in a minute, but this is, let me see. I've got a question for someone. Let me see who. Marquez, how are you today? Hopefully you're there. What can you say about this point? The velocity of the object at that point, at its highest point. What can you say specifically about the x component of velocity at that point? Now I'm going to draw it in. Maybe it looks something like, well, I can tell you what it's going to look like. It looks like this. That's a hint. So it's horizontal. It is about that. So that's the total velocity, sure. But what can you say? What else can you say about that? So v, so yeah, whatever, v at that point. But what else can you say about the velocity of the object at that point, Mr. Grayson? The x velocity specifically. Marquez, are you there? Joel, are you there? Joel?
Can I answer?
Go for it, Kareem.
I would say that it's at its peak.
What does that mean?
So what
It's
I'm
certainly
saying,
is at its peak.
yeah, what I'm trying to say is, I'm not sure if it's correct or not, but I'm just saying that like the velocity would be at its maximum over there.
Why do you believe? Oh, someone going to hi, you want to say something?
Yeah, I wanted for you to make a little discussion like between the class, like what this person thinks, what other person thinks, and I wanted to say like I think it's not its peak.
You think it's not what?
I'm saying like I think it's not it's max, the velocity of that function. Like he said that he thinks that it's at its max, and I'm saying like it's not. Then another student maybe says like it's at its minimum. I don't know. Another student says.
What are you saying?
I'm saying that it's zero. At its peak, I think at the beginning velocity, it's when it's at its peak.
One more time. You're saying the beginning velocity is when it's at its peak? What?
Yeah, I'm saying the beginning velocity is the fastest velocity. At the part you marked, it's just zero.
Okay. There was someone that had just raised their hand a minute. I was waiting for I to finish. Who was that? The Maximiliano. Comment, Maximiliano?
Yeah, I also think that at its highest point in parabolic motion, the velocity at that point where you have drawn is also zero.
Let's go with that moment for a minute. What does zero velocity look like?
Object that's not moving at all.
Yes. Awesome. Awesome. So, for example, with free fall, when I throw an object straight up, there is a point where the velocity is zero. Where is that point? Anyway.
At the highest point, right before it starts to fall, but it reaches its maximum, like going from the bottom up, that little max point, which is also the point where it goes from
That y
top
equals
down.
0, right?
Why don't you finish Maximiliano, and then Kenna, you can
Okay.
you can give what you said. Yeah. Go
So
ahead.
yeah, hi. Okay, so you're throwing it. You have it in your hand. You throw it up. It forms like a parabola. At the very top of that parabola that it formed, that is where the velocity is 0 because it's neither rising nor falling.
Well, I agree that the velocity for free fall motion in this case, this kind of free fall, the velocity is 0 at the top. It does not form a parabola, at least not in space. You might be able to see that in time, but maybe that's what you meant. But it's just going up and down, so that's not a parabola. It's just basically a straight line and following that straight line up and down in space, in x, y. Yeah, you could say maybe in t it might be, but we're talking about x, y right now. So, and yes, at the very top, it is 0. And how do you know that? Well, because it changes direction. If the thing has a non-zero velocity while it's going up and then starts to fall down and increases velocity, at some point in there, it had to be 0. And that point is, when you take the limit as delta t goes to 0, it's the very, the point where that instant where it changes direction is where the velocity is 0. So agreed. I think that's probably where you got it from. Now, Kimberly, you were gonna making a qualification or adding in something. What were you saying?
No, honestly, I was supposed to be on mute. But I think it's at the point y equals 0, but I'm really supposed to be on mute. That was asking. I'm sorry about that.
Well, y is equal to 0 is down here at the bottom when where it leaves my hand. Generally, if you're assuming, like when we do a,
I mean, at the top of the parabola.
are you talking about, what are you talking about? Like the example
At the
in my
maximum
hand or
point of the parabola. At the maximum point of the parabola.
right here? You
Yeah,
see where my
that's
finger's
correct.
pointing? Okay, so that's what Hayek was saying, is that the velocity is 0 at that point. But I'm kind of addressing that issue, and I'm addressing it by giving this class example where we threw something up straight up and down. So that's kind of probably where you're getting that intuition from, that's not I wouldn't say it's an unreasonable answer, but this is not the same situation as this. Why? Because in this situation, when I just throw it up, I don't have a horizontal velocity at all. And the thing that we have to get accustomed to when we start to look at 2 dimensions is it really is motion in 2 dimensions, 2 directions combined. So if I were asking you, what is the y velocity of this object at that point, I would agree with you. It is 0. Because when we look at the y motion of this thing, basically it's just this, straight up and down. But when we look at the x motion is constant velocity, at all times throughout the path. So that for 2 reasons, I can say that I disagree that the total velocity of this object is 0 at that point. 1, basically because of what I just said, that, yeah, the y velocity is 0, but and why we know why it's 0, because it's 0 for the same reason this is, because as it's moving up, gravity is slowing it down. And it slows it down to a point where it stops, and then it starts to speed up again in the opposite direction. That's what the y motion of this thing is doing. If I had a finger over here on the axis, and my left finger and my right finger is looking at the motion along the parabola, my finger is the y velocity. Goes up, stops, then comes down. Goes up, stops, then comes down. Same motion as if I just threw it up. In the x direction, it's moving along like you do when you're in your car going at a constant speed on a flat surface. Your velocity is not changing. Your direction, neither your magnitude. So if I put my left finger along the x-axis and follow, as my right finger follow the path, this is what the x motion looks like. So what I would say then is I would kind of guide your thinking to suggest that at this point, it is the y velocity that's 0, but the x velocity is not 0. And therefore, the total velocity in this case is the x velocity. The total velocity of the object actually is vx naught. Now, let's take that one point and see if we can quantify that by going back to these equations. What is the angle of the velocity relative to the horizontal at that point? Anybody? Well, it's pointing in that direction, and the x direction is that direction. So what is the angle between that velocity and the x-axis?
0
Anybody?
degrees.
0 degrees. If I take that and place it back into these equations, look at what I get. Sine of 0 is what? Anybody? You have to plug it into your calculator to do it. What is
0.
the sine of 0? 0, which means that if this equation is defining the y velocity, vy naught equals v naught times the sine of 0, that's telling you that the y velocity is 0 at that point. What is the cosine of 0?
1.
1. So this equation is telling you that Vx naught is equal to V naught times the cosine of 0, so that Vx naught is equal to V naught. And that's what I'm showing you at that point. So good effort. Definitely studying, trying to learn what use what you learned to apply to this. But there's these subtle differences that oftentimes occur, and this is one of those kinds of things that occurs with parabolic motion. That if you're just talking about the y motion, Kimberly, hi, all the people who said 0, your logic is correct, but only for the y direction. What the criteria is pointing out, right? In the y direction, ay is negative g, so it's just like any motion that you've already previously studied about for just motion in the y direction. But this is combined motion, and something else is going on in the x direction where the acceleration is 0. And again, when the acceleration is 0, since the acceleration is defined as change in velocity, that's saying the velocity is not changing. So if it has an initial velocity in that direction, it's not changing. So in the x direction, the velocity is constant, which again is what that is saying. So at that point, since the total, and let's go back to this, because there's another way we can see it. Since the total velocity at any point, whether here or here, I didn't finish here. That's what this, what this is saying. So at that point, we've already determined that because the angle is 0, the y velocity is 0. So what that's telling you is that the total velocity is just equal to the square of the total velocity is just equal to the velocity in the x direction, the square of it. And so when you take the square root, again, you're back to that the total velocity is equal to the x velocity at that point, at the highest path. Any questions about that before I continue with the next couple of points?
No questions.
Okay. I went past the break. So I don't want to overwhelm you. Let's go ahead and take a quick break right now. This is going pretty well the way I want it to go. When we come back, I'm going to finish up with symmetry associated with this picture. And then I'm going to get to the physics, because this is just the geometry. It's just the geometry of this problem. But we still got to do the physics. So let's take Yeah, so what we're saying, I was going to finish up the symmetry and then get on to deriving physics equations properly. So symmetry, what goes up must come down. That was a song back in the 60s, or well, I've looked at two different points on the opposite side of the top. But if I were to look at points that are kind of symmetric to those points for the object as it moves down its path on the other side of the parabola, there's going to be a point on this side that is consistent with the height above the ground, whatever that height would be. And of course, this last point is just back down here at the bottom. So, and what we see is symmetry. Again, we're excluding drag, so there's no energy being taken out of the object as it moves along due to friction. So at this point, it starts to pick up velocity again. And you would assume that when it's at the same height going down, even though we say the velocity is different because the direction is different from the velocity it had on the other side of the path, the magnitude of that velocity would be the same. And therefore for each of the components as well. So here, we're looking at something that looks something like that as being V total, and then Vx is going to be the same value as it was on the other side, Vx, and Vy, and Vx, of course it is, because we just finished saying that Vx doesn't change. It's the same everywhere at any point along the path. Vx. And again, these equations apply for that position as well. And then again, coming back down to this point here, when we're back down on the ground, we can compare it to the values, the magnitudes, as it are comparative to what they were in the beginning. So when we're back over here, we now have this scenario here. Yeah, so it's not the initial velocity, but it has the same magnitude as the initial velocity. And all the components, everywhere along the path, as we said, the components at the same height on either side of the parabola would be the same, the magnitudes of those components as well. So, get this down, let's complete that. Yeah. And so we have these scenarios in there. All right, so that's the geometry, symmetry, trigonometry associated with that. Now, as we had said earlier, since we have acceleration in the x direction, in the y direction and none in the x direction, if we look at our general equations of motion, general x, general y, and free fall, we already determined that of those equations, the general forms that survive based on this criteria are these. Now I'm going to number these just straight up. That the velocity is equal to, and this is, this was in the x direction. Velocity in the x direction is equal to initial velocity in the x direction plus, no, sorry, what am I saying? Not velocity, it's position. So equation 1, the position in the x direction is equal to the initial position in the x direction plus Vx times t. Now, what you can see about this equation that I didn't say yesterday is I could have just as easily placed Vx naught here. It doesn't matter because the x velocity is the same everywhere throughout that motion. It doesn't matter, velocity is constant. So that equation applies. However, what I didn't say, or I don't know, whatever, is that what I did say. I said that this equation, even though it looks the same, it's not quite the same as the one for one-dimensional motion because of these now. This Vx or Vx naught, it doesn't matter which one is, it's actually equal to V, well, this guy is equal to V naught times the cosine of theta. So if I wrote this in its expanded form, it really would look like this. And it would be x is equal to x naught plus V naught cosine theta naught times t. I don't like to do that. I like to separate it like this. It's just the way I have it formulated in my mind. But we have to keep that in mind that I'm going to erase this, right? Well, I'll keep it for now, whatever. But really, I kind of count this as the equation of motion. But for two-dimensional motion, I have to understand that this Vx is really a little bit more complex than it is in one dimension. And we can say the same thing for the other four basic equations for parabolic motion as well. I am going to erase it because I want to kind of, in the end, I want to have just, well, whatever. Yeah, we'll keep it there. And we'll summarize in the end. So what were those other three? Well, they were for the y direction. Vy equals Vy naught minus GT y equals y naught plus Vy naught times t minus 1/2 GT squared Vy squared equals Vy naught squared minus 2 GY minus y naught. And finally, y minus y naught equals 1/2 Vy naught plus Vy times t. Again, focusing on how I introduced this as combination of constant motion in the x direction plus free fall motion in the y direction. So that's where we can just extract these equations. This is bothering me. I'm going to take it out. I just wanted to be clear. I guess I remember it now. But again, as I was saying, for these as well, you got to be careful. Vy naught is actually equal to V naught sine theta naught. Here, 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 here. And also Vy is equal to V sine theta, right? And so we got to be careful about those velocities. Now, what I say to students is that these equations, these are the 5 basic equations for parabolic motion. physics equations, and they are annotated or further described by their geometric relationships here together. Now, in the book, you might see them written together with this stuff inside there. I just, we've explained it comprehensively here, I think, fairly well as an introduction. So I like to keep the physics and the math separate. That's something that I told you before. I just am reiterating that now. That's how I organize it. But there are two other equations that we have to do a little work to get to the other two equations that define parabolic motion. One of them has it doesn't have a name. I call it the y of x equation. And the other one I call that does have a conventional name, and it's called the range equation. And I don't want you to confuse the two. They're not the same thing. Now, any questions before I derive for you the y of x equation? Any questions about what we've been talking about? Okay, now, one of the comments earlier reminds me of something. I'm going to use that at this point. I forget who it was. It might have been either I or it was Kareem. I'm not sure. Somebody talked about the fact that when I was throwing this ball up, they said that it followed a parabolic path. Or no, they just said parabolic. You didn't qualify. And so I qualified by saying, okay, because the context was the path. I said, okay, well, the path is not parabolic, although you could describe it as being parabolic in time if you looked at, this equation here, right? The y, but that's y of t, not y of x. Parabolic motion gets its equation from the actual path, the fact that the path itself, y of x, is parabolic. And actually, with the basic equations, that's not obvious. You don't see that. It's not this equation. This is a parabolic equation, but in time. When people refer to parabolic motion, they're talking about space, the path of the object. So it's parabolic in space. So where does that come from? We should be able to see that mathematically. And the way that we can see that is, one, what we know that connects the two, even though these motions are physically separate motions giving rise, that arise because of different physical circumstances in the x direction and the y direction, even though we're talking about the same object. One thing that does connect the two dimensions is the ultimate independent variable, time. Right? Let me go back to this scenario here where I was doing the thing with the fingers. Right hand follows the path. Left hand will either follow x-axis or y-axis. The velocities are very different, right, at these different points. But what is, the unifying variable is time. And time isn't on this graph, right? This is y of x, so it's not really explicitly being shown here, time. But however, what I can say is that when my right hand is at the maximum height along the parabola, my left hand is at the maximum height along the y direction. And that happens at the same time period. Similarly to the x-axis. Right hand is following the path, and left hand is just moving along the x direction. But we can say that when the object is at its highest point, the left hand along the x-axis is midway between the range, the total x. But that happens, those 2 points are occurring in x and in the path at the same time. So the point is that even though these are describing separate motions along different coordinate directions, the time in the equations represents the same time relative to these two different directions and any equations that you could compare. So what I could do to find the parabolic equation that defines this type of motion is if I solved, also notice that by the way, that I didn't put any subscripts on the t when I wrote out the equations. There's subscripts on everything else, defining its direction along what coordinate direction it's along, and also with just the variables, but I didn't do that for time. So if I solve equation 1 for time and substitute it into equation 3 and do some algebra, that will give me it will convert equation 3 to an equation that's parabolic in time to an equation that is parabolic in x, y of x. Right now, this technically is y of t. I've relaxed the independent variable just for the purpose of writing it out nicer and saving some ink in my effort in my hand. But this is really the formal equation, all of these. Whatever variable it's solved for out in the front, that's y of t, or v of t, v of t here squared, and y of t minus y naught. So, yeah, so what I'm going to, and so when I do that, it's going to convert this equation to a y of x. And that would be the parabolic equation that defines the motion. So, I'll call this 1a, or 1.1, I'll say, 1.1. Solving it for t is going to be equal to x minus x naught over vx naught, okay? So if I take that, and everywhere there's a t in this equation, I stick that, then we're going to have a bunch of algebra, and then we fix it, we do the algebra, and then we have thing. In fact, maybe I could do it down at start. So I'm going to stick equation 1.1 into equation 3. When I do that, I've got this. Okay, so I've got y equals y naught, which is, so y naught plus vy naught times t, but t is this guy, so that's going to be v y naught times t, which is x minus x naught divided by v x naught. Okay. And then minus 1/2 g x minus x naught over vx naught quantity squared. Okay, I'm gonna have to erase some things here. I'm gonna erase this stuff. Don't want to erase the picture just yet. Hope I can keep it to the end of this presentation. Ouch. So I had an outpatient operation on my shoulder last Tuesday. Got some bandage and it's starting to itch now, kind of like a car. Okay, simplifications here. Now what I'm going to do is I'm going to go ahead and put in the trigonometric stuff during this simplification. Got to put it in now. So here we're going to have y minus y equals y naught. And then vy naught is v naught sine of theta naught plus v naught sine theta naught. But then I have so I have that over vx naught. But vx naught is v naught cosine theta naught. So I'm just going to put that on the bottom here, v naught cosine theta naught. And then what I have left is x minus x naught. So I'm just going to multiply that over here, x minus x naught. Got that like that. Now, minus 1/2, and that's still, like I can bring the v naught squared out, but it'll be something like, I could do it like this, minus 1 over 2g v x naught squared, and over here that's x minus x naught quantity squared. Hopefully you can see. quantity squared. Okay. The V naught cancels. Sine theta naught over cosine theta naught is tangent theta naught. We have y equals y naught plus, that's going to be tangent theta naught. And then this becomes x minus x naught. Now over here, I didn't substitute in. Now I want to do it now. Guess I could have done it here as well. But Vx naught, again, is V naught cosine theta naught, but it's squared. So that's going to be minus x minus x naught quantity squared over sorry, the brain part. This is g in the numerator. Oh, I did that. So this is going to be minus g over 2, and this is going to be v naught squared cosine squared theta naught. And then, of course, I just have x minus x naught quantity squared. Now, I like this version here. I like to keep it like that, so I'm going to box that in. But you can see if I'd apply that to this problem, in this problem, x naught and y naught are 0. So if x naught equals y naught equals 0 for a kind of a perfect, starting at the origin, then this equation reduces to this guy. That y is equal to tangent theta naught x minus g over 2 v naught squared cosine squared theta naught x squared. And you can more clearly see there that that's a parabolic equation. And you can see it here too, but more like what you might see in the math. So y of x equals that. So that's the equation that defines parabolic motion, because if you were to graph this, put this in, what's that graphing software that a lot of you guys use or students use? Desmos, yeah. So you could very easily throw this in Desmos, or something, any graphic, and it's gonna, what it will give you is this path. It's a parabolic and you can see it's parabolic in space in XY. Yeah. I think did we already review that? Yeah, we reviewed the parabolic equation. I think I'm not mixing up with the sum square. We reviewed that the first week of fall. So yeah, and so you would apply the parabolic formula to get that, to solve that if necessary. So in addition to these first 5 equations, this is what I call the 6th equation for parabolic motion. And I call it's just the y of x equation. These, I box all these in. These 5. 1, 6, no. Would it work? Yeah, right. So these are the 5, and this is the 6th equation for parabolic motion. And again, that came as we're combining 1 and 3 over here. Now, any questions about that? Okay, now the 7th and the last equation that defines the concept of parabolic motion, physics equation that defines it, is something called the range equation. The range equation. Now it takes the range equation is actually a really nice equation. it's a little bit more elegant, right, than all of these. Elegant, what does that mean? You've ever heard that before? There's this physicist up in San Francisco, Michael Green, about 20 years ago, came out with this television show special and a book called The Elegant Universe. We talk about equations like E equals mc squared. Well, E equals mc squared is definitely the most famous equation, but it's also somewhat elegant itself. When we use that term in physics, we mean kind of like poetry. The reason that poetry is generally considered more powerful, a communicative expression than prose. And even when we say that there are prose or speeches that are really powerful, we refer to them as poetic. So just a little digression here while I rest. To talk about elegance, what that means is that we're talking about power. And well, we haven't defined power yet. We're going to do that probably in chapter 6. But power is related to energy, but it's different. It's how much energy is exerted or done in a certain amount of time. So if you have 5 joules of energy and you expend that energy over 10 seconds, and then later on you have 5 joules of energy and expend that energy over 2 seconds, the same amount of energy was dissipated or used, but because one energy was done in a shorter amount of time, it's more powerful. And so based on some physics associated with impulse, it can deliver more power. And think of a bomb, right? Bomb gets all of its energy out in less than a second, or maybe even less than a tenth of a second. And it can do more damage. So elegance is really about that. But you might say, well, we're not talking about quantum physical terms. How can a language be powerful? What does that mean? Like it's, what are you're not expending energy, right? It's not inherently being expended just because it's being written or something. I don't know. I have to talk about that. But it's really about meaning per words, the number of words stated. And it's actually, you might think this doesn't have anything to do with physics, but it actually does. Quite related. The fact that, some people say, and this is a little bit more advanced discussion from Physics 39, if you stay with me. At some point, the whole point of this class is, what does it mean? Why are we doing it? Now, at this level, it's not so obvious because you're doing it because you need to learn physics to get the next course. But why do we study physics in the first place? Like, what's the purpose of it? Yeah, so we can build things and understand things. Sure. Once you build the thing, then what? Right? Ultimately, there's always another why. And the ultimate holy grail of physics is, people have made movies about it, right? The theory of everything or grand unification. It's had different names. Even Oppenheimer, I think at the end, go to see that movie, they were focused on building a bomb. But even he had kind of a crisis at the, you see that in the movie. So once he did the thing, then what? Was it just to blow a bunch of people and kill human beings? That's the whole point of all this brilliant science, is to kill people. What does it mean? Right? So ultimately that takes you to, what is the universe? Why are we here? What is this about? And when you get to that level, what some answers that people are giving is you might hear of the term the holographic universe. We're living in a hologram. Nothing, reality is not what it seems. When they're saying that, they don't really mean a hologram in the sense of what you probably think of as a hologram. It's more of an analogy. But the point is that one of the things that people are saying is that everything is just information being expressed in different ways. And we perceive it in those different, again, perceptions. But it's literally just information. I know that's kind of hard to understand because we think about information on a page or on a data sheet. How can the universe, how can this, a strand of hair be information manifesting or projecting? Well, again, we need to get to quantum mechanics and stuff to talk about that, but it could in fact be that what we're seeing as our reality, there's a couple ways to explain it, but it might just be a projection from information projected from a higher dimension. We talked about what a dimension is, onto this 4-dimensional universe in which we live. Space-time, 3 dimensions of space and 1 dimension of time, although time is just space, actually. It's one way there's one way you can explain it. I'll do that later. That it's not space and time, it's more like space is time, but time is like a 4th dimension of space. Anyway, the point is that our perceptions are, we say 3-dimensional, but it's really 4-dimensional. If you could include space-time, how Einstein defined it. And what all we may be seeing, everything we see is really, it might just be information manifesting, from higher dimensions onto what we see in 3-dimensional. Remember the analogy I gave you last week about the 2-dimensional person. And when I project this, this ruler onto the thing, you look at all the characteristics of this ruler, but all this guy sees on the shadow, he doesn't even see the thickness of the shadow. The only reason you can see that is because you're looking at the 2-dimensional from the 3-dimensional. The only thing that 2-dimensional person sees is a line, and the line just gets shorter and longer as I do this, way this back and forth, right? And what are we expressing? This is kind of another way to kind of maybe talk about why I'm calling it information. If that dude, that 2-dimensional dude, wanted to characterize the line, the only thing that he can do is measure it and measure how it changes. But we know that equation, that number that he's measuring, it's equal to the length of this thing times the cosine of the angle that this thing is making with his 2-dimensional world. So in that way, I can describe that thing that he's seeing, which for him is real, as just a mathematical equation. So that's what I mean, that everything can be just like described as information, particularly when you're looking at it from a different, maybe a higher dimensional perspective. So, a bit of a tangent there, but elegant equation is referring to the fact that some equations are kind of more powerful than others. I said that about this guy, right? It's more powerful because of its mathematical prowess, or it has the quadratic equation associated, the quadratic formula. So when I manipulate it, I have more options of being able to manipulate it in different ways. And so I can extract more information from it than maybe these other equations. Now, people don't necessarily refer to this as an elegant equation because, parabolic equation, it's powerful, but it's not like, But with some equations like, E equals mc squared, there's so many different points of view and perspective expressed in that equation that it says more with less. So that's what we mean by elegant. When we're talking about elegance in mathematics and science, it's talking about how much information can you compress in this one representation of a physical concept. So there is a bit more responsibility associated with using that, because usually with the more elegant the equation, the more finesse you have to apply in using it and applying it correctly. We'll continue that conversation, at some point later. But let's not take this back to this guy. The range equation is somewhat more, probably of all of these 7 equations, including the range equation, it's probably definitely going to be the most elegant because it has a lot of information in it, or at least more than the others, compacted. But you have to be careful how you use it. You have to understand the criteria. Now, what is a range? A range is just another word. It comes out of military history. These equations for parabolic motion are important for people who, warriors who are in artillery. Napoleon, for example, was actually quite an exceptional mathematician, and he used that to kind of go up the ranks in the military, and then did a coup and took the country. took it out. Well, he saw an opportunity during the revolution and used that to the destabilization of the government and the fall of the government to take control of the military. But the point is, I digress again. But the point is, he was an adept mathematician, and he was artillery, so he could nail you with a cannon, you know, and that was, you know, and basically he used these equations. So range is a term that comes out of the military. When you have a cannon, you want to shoot like an artillery shell downrange on a flat warfield, like they used to do back in the day. You know, you got to hit the target. So delta X for a situation where you're on a flat surface, like a battlefield, delta X is referred to as the range. So it's like downrange, right? It's the distance away from the X distance away from the initial position where the shell hits. So range mathematically is defined as, where the symbol is R, and we define it as delta X. Now, the range equation is a special case of the y of x equation whenever, what I say is, you have a perfect parabola. And you have a perfect parabola whenever the initial y position equals the final y position. So under the criteria that delta x becomes r and delta y is equal to 0, remember delta y is y final minus y initial. So whenever on a parabola y final equals y initial, the parabola between those 2 points maps out a perfect parabola for that specific range. So under that criteria, all I need to do is take this criteria and substitute it into equation 8 for the the y of x equation, and do some algebra, and that converts the y of x equation to a special case of the y of x equation, which we call the range equation. So let's do that. Let's substitute this criteria into here. Now, I'm going to take the y naught and bring it over so that I actually have delta y. So delta y equals tangent theta naught, but delta x is r. I'm just going to put r there. And now I have this term, minus g over 2 v naught squared cosine squared theta naught. And then I have, r squared. R squared is delta x squared. Okay, let's do the algebra then. Finish the algebra. Well, delta y is 0, so that guy's out. So that leaves 0 equals, now I guess I can cancel out an r2, right? Because I have 0 equals tangent r minus r squared. So one of the r's goes out. Just divide through by r, the whole equation. That becomes 1, and that becomes r to the first power. So what I'm left with is this thing. And so I can solve that. Well, I'll do it in a couple of steps. So 0 equals tangent theta naught, minus g over 2 v naught squared cosine squared theta naught, and then times r. Okay, so let me solve that for r. If I do, I'm going to have, so tangent theta comes on the other side, or negative tangent theta, theta naught. And the minus signs will go out because, you know, well, I'll cancel in a second. Oh yeah, sure. So minus equals minus the stuff in parentheses times R. So they may become positive. So then I have to kind of invert, cross multiply on this thing here in the parentheses. G over 2 squared. The cross multiplying, I'm going to get 2 V naught squared cosine squared theta naught times tangent theta naught. And then I have to divide by the G. Divided by G equals R. Okay. Still got some algebra here to do. Tangent theta naught is, let me do it over there, use the space over here. So I'm going to have 2 V naught squared, and I've got cosine squared theta naught, then times cosine, so sine over cosine. So that's cosine squared over 1, then sine theta naught over cosine theta naught, and then all of that is over G. So over there on the right, I've got one cosine that cancels, that leaves 1. It cancels that whole guy. So when I simplify that, I end up with R equals V naught squared. The 2 is still there, but this is going to be 2 times basically sine theta cosine theta naught, or cosine sine. I'll write it like this: sine theta naught cosine theta naught, all of that over G. Almost home free. Now, what we use is a trigonometric formula for this guy. That is one of the, I think I reviewed that the other day. That's one of the double angle formulas. Does anyone recognize that? Double angle formula for sine. Anyone? I want to keep those up there, so I'm going to erase the picture. Double angle formula is these guys. What is it? Sine. So let's make it some math formula. Sine. Sine 2 theta is equal to 2 sine theta cos theta. And there's some others for cosine. I'm not going to write those out. I'm going to need them. Double angle formulas. So basically, I just substitute that in, sine 2 theta. Now remember, in the double angle formula, it literally means double angle because in the argument, it's 2 theta. I'm putting that in, so it's not outside, it's inside the argument. So the final result for the range equation is that the range, the distance downrange, is going to be equal to V naught squared times the sine of 2 theta naught over G. And that's the range. But again, I'm going to stipulate the criteria that because when I started this equation, I had this criteria and I plugged it in. We can't forget that. This equation only applies, you could only use this equation when you have a perfect parabola, when delta y is equal to 0. So this is under the criteria that delta x equals r and delta y equals 0. So now it becomes the criteria by which you can only use that equation. Really, the y parameter is the governing parameter. Delta x is just the definition, delta x being r. So those 7 equations comprise the the equations of motion for parabolic motion. So those things, along with the geometric relationships that I described to you, is what I would call the concept of parabolic motion. So that's what I'm referring to there. Okay, I want to announce a first test. I mean, to make you panic. Next week. Probably, it won't be an in-class test. I'm gonna let this be our take-home test, home test. But I'm probably gonna open it on Tuesday. And actually, let's see. Yeah, open it on Tuesday.
Tuesday,
And
you mean tomorrow or next week?
Next week.
Okay.
Open it on Tuesday, and it'll be due. You have probably a couple days to get it done. So open on Tuesday or Wednesday, and you have a couple days to do it and turn it in. And it will be on the first 4 chapters, the combination of one-dimensional and two-dimensional motion. So I know we got some work to do between now and then in terms of recitation problems, because I want to do some work out some class problems to do here. But this is basically the basic block of information, the basic information that is, you know, if I were to structure like a summary, it would be general motion X, Y, free fall motion, and how I wrote those out and the equations associated with those. And now this parabolic motion. 7 equations for parabolic, 7 physics equations, plus the trig equations. And of course, having the picture kind of maps out the pictorial representation of the path of the motion as it moves along. And there's other things, right? There's, you know, the area under a curve. There are some graphical implications of one-dimensional motion and some things. But this is the basic concepts and the basic equations that describe those concepts. And this is it. This is parabolic motion. So, what time is it? That's 40 minutes. So probably the best thing at this point is to, you know, do a couple problems, you know, with to illustrate how to use this. Maybe I should go ahead and get that in now. And then I can spend Wednesday like working. Maybe I can, yeah, spend Wednesday using those and looking through problems. Yeah. Yeah. So I'll do it. I don't know what I'm going to get that motion. Because that would be, that's actually, so that's, this is the 4th type of motion, centrifugal motion, we call it. Would be 5th. Yeah. So in the example that I gave, where I flicked the penny off or the quarter off, you cannot use the range equation for that. And one of the reasons I'm stipulating or emphasizing the criteria is that if you use the range equation for that problem, there's nothing here that's going to tell you you're getting the wrong answer. You just have to know not to use it because the criteria is not applied. It's not a perfect parabola. That's why I like to use that term, because it just jumps out at you, right? You would have to use the y of x equation for that problem. In fact, the y of x equation you can use for anything. Anything that you use the range equation for, you can use this and get the right, get the correct answer. It's just that it would take more work algebraically. And as I just showed you, this actually comes from this equation anyway, under the stipulation that delta y is equal to 0 and delta x equals r. So that's just one way to kind of think about that. Now, one thing that's nice about the range equation is that there's some symmetries in this thing. Let's take a look because of the trigonometric relationships between those trigonometric relationships that I talked about earlier. What we see, and again, someone like, Napoleon was a master of this, manipulating this on the battlefield. That's good or bad, but it is what it is. History. Maybe these are the cannons that he used to destroy the library at Alexandria. Although I used to think he did that, but I heard something recently that it wasn't him; it was the civil wars in Egypt and the Egyptians did, not Napoleon. I mean, what am I thinking of? No, I'm confusing Julius Caesar with Napoleon. So no, scratch that. Anyway, what am I saying? Yeah, so let's take a look. This thing has some symmetry. It turns out that what you show is that if you have a set velocity, like say you have a cannon and it only gives you it can only shoot one initial velocity. Well, you can manipulate how far the thing goes if you understand this equation. You can manipulate it very easily. First of all, you see that when the angle is 45 degrees, because it's a double angle formula, you get 2 times 45 is 90. So at 45 degrees, the sine of 90 is 1, and you get a maximum range. So the maximum range occurs when you're throwing something, and this applies to artillery, but it also applies to like anything, throwing a ball, throwing a football, kicking a football. If whatever power and speed, you can throw it, initial speed you can throw it, you're going to maximize your range if you throw it at 45 degrees. It's going to give you the maximum range. So I'll start off with a picture representing 45 degrees. No, that's 90, 40, so 45 might be something like that. And so if I shot the thing off at that, I'm going to get a parabola that might look something like this. It's not perfect, whatever. Now, let's say that I go up to a total of 30 degrees. So for 30 degrees, that's lower than 45, the object is not going to go as far. It might do something like so this represents, you're going to see something like that. It's probably somewhere in your book, 45 degrees. And they might use a different color to represent 30 degrees. So 30 degrees, I don't know. Maybe it does something like this. Call that 30. But there's another angle that's going to give me the same range. However, the time will be different. And that's going to be the angle that's the complement of 30 degrees. The complement of 30 degrees is 60 degrees. So at 60 degrees, I might get something that looks like this. It has the same range, but it takes longer for the ball to get there. This is 60. And any combination of complementary angles will give you a scenario like that. So, something like, I don't know what the shortest thing would be. I don't know, but something like 10 and 90, 10 degrees and 90 degrees. 10 degrees would be, I guess, is infinitely short. That's the answer to that question, because you can always break it into smaller and smaller. Yeah, so an infinite, so 10 degrees might be something like, that, I don't know, like that. But then at 90 degrees, you're going to go really high. It's a long time to come down, but then you're going to hit the same thing. 10 degrees. And 90 degrees. Yeah. And I think sometimes they show 70 and 22, something like that. But yeah. So all that comes out of understanding the the range equation. All right. Mm. 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 We'll talk about too much. Yeah. So yeah. So to summarize, we still got it here. These 5 equations. I'll summarize in general for everything a little bit this week, maybe not today. But I knew where I'm going somewhere. Yeah. Yeah, so we've got equation for the x direction, the basic equations for the y direction, keeping in mind that for two-dimensional motion, we have the trig and geometry associated with the velocities. Okay, so I've erased those equations already. Yeah. We've derived 2 more equations, the y of x equation, which probably of all of them, I don't know, I said that Rx is more elegant, but maybe it is, but this is, it's special, right? It's not, you can only use it under certain situations, but this is definitely by far the most powerful equation. I don't know how elegant it is, but it's definitely powerful. Elegant means sometimes with elegant, there's a certain ease of use, whatever. It's just qualitative mumbo jumbo. But this is the y of x equation, right? Where you're writing y in terms of x and you've converted it, the equation 3 to that because of substituting in equation 1. That's how we derived it. So y of x meaning y of x equals all that. Let's say 7 or 8. Okay. And then from that, we can put these special stipulations on, these criteria, and from that we get the range equation, which is kind of easy to use. It's kind of a simplified version of y. But you can only use it under criteria and whatever. Yeah. Okay. I do want to work some examples, but I think I want to go ahead and get this in out of the way quickly. It's only take a few minutes. It might be the best use of the time because parabolic problems usually take a little bit longer. So I can go ahead and get this in, and then we can give us more time on Wednesday. Actually, do this big problems as well. All right. earlier today, I was twirling an object around like this. And talking about that. As it turns out, whenever I do that such that the velocity of the object is the speed of the object is constant, I can class that as a special kind of rotational motion that we have enough information that we can talk about right now. Rotational motion really is not until chapter 9 or something like that. But there's a simplified rotation, a special version of generalized rotational motion that we can talk about at this point, even before we talk about forces. Now, let me ask you a question to set up this demonstration. We know that velocity is a change. Velocity is defined as change in position with respect to time. And we've also determined that velocity is a vector. It has both magnitude and direction. Now, so yeah, that's velocity. Sorry, I'm talking about. So yeah, that's the definition of velocity. Acceleration is a change in velocity with respect to time. So with a velocity is constant, the acceleration is 0. We talked about that. Well, I've erased the picture already, but in the criteria for parabolic motion. So when I tell you that I can twirl this object around such that the speed, and by the way, we already determined from these pictures that the velocity is tangent to the physical path of the object for any object, no matter what kind of motion. And we also determined last week when we were talking about vectors and scalars that speed is the magnitude of the velocity. So what I'm going to tell you here is that I can twirl this in such a way that the speed of the object around its circumference, the circumference being the length of the circular path that it's mapping out. If the speed is constant, what I want to ask you is, does that mean if this is constant speed, what I want to know is, does this object have an acceleration? Does it have some kind of acceleration, even if its speed along its path of motion is constant?
I don't think so.
Okay, Maximilian, so let's do one of those things. Here you go. Whoever wanted that, I didn't do it earlier, but I'll give it to you now. So Maximiliano says no. Show of hands. How many people think something rotating at a constant speed, does it have an acceleration or not? And if it does, if you say it does, I want you to explain to me why. So show of hands, people who don't think this is accelerated. Moving around at a constant speed, is it accelerating? So 1, 2, green, Arnulfo, Kevin, Cox. Okay. Okay. All right. So I only got about 4 people. What about everybody else? Who thinks that this thing is not so? I don't know. What did I just say? Is accelerating? Yeah. So who thinks it's not accelerating? Does that mean everybody else, or is people not participating? Show of hands for people who do not think it's accelerating. So Kareem, so again, like some of those are the same hands that were up, or did I just have a dyslexic moment? I don't
Wait,
know.
I'm confused. You said if it's not accelerating or if it accelerating.
Yeah, so let's go with this thing has a constant speed. Is it accelerating? Yes. Show of hands. Constant speed. Is it accelerating? Yes. So I got like 3 hands, Kareem, Mikey, Armand. Now, people will say, no, it's not accelerating. Who are they? Kevin, Arnulfo, Katie, Maximiliano. Okay.
Professor, I
And
have a question.
Rach. Yes.
I've only known acceleration as like change in speed, right? Does
Mhm.
acceleration only affect change in speed? I want to
Uh,
say.
well, that's a good, it's glad you raised that issue. The
Good.
acceleration is, that's actually not the definition of acceleration. It's not change in speed. The acceleration of the definition of acceleration is that it's the change in velocity. And there's a subtle difference there. What's the difference? You said change in speed, I say change in velocity.
Okay, I get it now. I want to change my answer then. It does have a changing acceleration.
It has an acceleration. And why do you change your answer?
Because the way I'm thinking, okay, velocity is direction and magnitude. When it's spinning in a
Yes.
circle, it's changing direction.
Awesome. 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 Yeah. Yeah. So even though its magnitude is not changing, its direction is changing. And because its direction is changing, it has an acceleration. Yeah. And as it turns out, anytime an object moves along a curved path, it has 2 components of acceleration. One that is tangent to the path, either parallel or anti-parallel to the velocity, right? Because if the magnitude is changing, then there's a direction of acceleration in the same magnitude as velocity. If it's increasing, if velocity is slowing down, then it's decelerating. So the linear acceleration is opposite direction of motion. But because it's moving along a curved path, there must be a component of the velocity a component of the acceleration toward the concave portion of the curved path. If you look at something like this, and so let's say that we have a curved path, and there's an object moving along from left to right. So at some point it has a velocity that's tangent to the path, as we've just been showing. That's v. Well, if the velocity is changing, at some other point we've got another, I guess I should. So say over here, we've got another velocity, its velocity is different. Maybe it looks like that. That's V1, this is V2. When we put these two things together, what we see is that the change in velocity is not so if I project this thing back down, let me just take it out. Like I told you, if I project a vector anywhere in the space, as long as I don't change the magnitude or direction, I still have the, I can really project it anywhere I want. So just kind of sketching this out. If this is V initial and this is V final, let's say 1 and 2, or initial and final, then what does the change in velocity look like? The change in velocity is going to be, that's delta V, and it's defined as V final minus V initial. Well, what does it look like graphically? Well, it's kind of like, this is not space and position now, but basically I have to move along this direction, the initial vector in the negative direction, and move along that guy in the positive direction. I have to do this and come back up here. So that's the same thing as just going from the tip of one vector to the tip of the other. Right? So delta V looks like that. So I guess what I'm trying to say, if I now project this back to either one of those vectors, it's really not, you know, well, let me do it this way. That's delta V. And if I project it back like I was about to do to anywhere on the, you can see that delta V points toward the concave portion of the curve. And we can look at different scenarios, whether it's, because I haven't really specified whether it's speeding up or slowing down. It doesn't really matter. If the velocity changes while it's moving along that curved path, which it will, you know, either by magnitude or direction, then you can create a delta V between 2 points on that path, and the delta V will always be pointing toward the concave portion of the curve. So that's a qualitative proof of that for what I just did. Now, by defining acceleration as a change in velocity per unit time, we did that last week, right? That's the average acceleration over delta t. And then the instantaneous acceleration, just taking that value and taking a limit as t goes to 0. Of the average acceleration. Either way, I can see from this definition of average acceleration, acceleration is also a vector, but delta t is not. So that implies that the acceleration gets its vector nature from the delta v portion. And I'm showing that the acceleration is proportional to delta v. In other words, qualitatively, I can have shown somewhat of a proof. It's not a proof, but it's a illustration, pretty clear illustration that delta v points toward the concave portion of the curve. But by definition, the acceleration is parallel to delta v, which means the acceleration of this system also points parallel to delta v. So I could just, from that, I could just write here anywhere in this space that whatever the acceleration is, I don't know its magnitude. You know, since I haven't specified any numbers, I can't determine its magnitude, but I do have enough information to know that it's pointing in that direction if these other things are right. Why? Because it's got to be parallel to delta v, which means that whenever an object moves along a curved path, its acceleration, the total acceleration now, not the linear or the radial, which we'll talk about in a second, but the acceleration is pointing toward the concave portion of the curve. Now, having said that, let's take a look at something. Again, let's just kind of qualitatively sketch out something here and look at that acceleration as that object moves along its curved path. I'm just going to redraw it over here. So I have, V at some point like that. Now, what I know is that from that point, it's moving along a curved path, in this direction. So because I've just talked about this, I know that there's some component of acceleration while this object is at that point that is pointing toward the concave portion of the curve. Even if it's moving at a constant speed, it's still has, well, if it's moving at a constant speed, then it's a special case. It's a circle, so the acceleration wouldn't exactly be. So in this case, the speed is not constant. Let's say that the speed is increasing, let's say. So increasing speed is V. Let's say V is increasing along that path. Well, I know that the linear component of velocity then has got to be in the same direction as A. So I could call this, if I drop a perpendicular back here, find a component, I'm going to call that A parallel, meaning the component of A that's parallel to V. But I could also define a perpendicular, which is a perpendicular component of A that is perpendicular to V, right? Making a 90-degree angle. That I'm going to call a perpendicular to the velocity V. So ultimately, then we can describe a parallel component. This parallel component is just the linear acceleration that we described, in the first couple of weeks. But this is what I want to talk about now. This perpendicular component is actually something called a centripetal acceleration. In general, the total acceleration of the object as it moves along a curved path has both a parallel component and a vertical component. However, whenever the speed is constant, a parallel is zero because the linear component is, the velocity along the path tangent to the curve is not changing. So in that case, when a parallel goes to zero, the total acceleration, because from this we can see that a total is equal to a parallel component plus a perpendicular component. But whenever v is constant, then that means that the linear component, a parallel, is zero. And so in that case, if I were to represent the velocity here, v, I now only have one component of acceleration, and it is like this, a perpendicular. In that circumstance, a perpendicular is equal to a, the total acceleration. And this is a special case because if that's the case, that means that this object is moving in a circle. It's kind of a messed up circle. And just to be complete, let me finish this out. Whenever v is still moving along a curved path, that's v. But what if v is decreasing, it's slowing down the velocity? When v is decreasing, then the components of acceleration are such that a parallel is negative. So it's opposite the direction of the velocity. But I still have to have a perpendicular component. So that means that the total acceleration would look like that. All right, so that you still have your a perpendicular, but now this other component makes the total acceleration look like that. And so what we can do, sometimes you talk about the angle that the total acceleration is making with the with the velocity. Under situations where velocity is increasing, if I were to define this angle here, let's call it, I don't know, phi or something, this angle right here, phi, then under this case, phi is acute. Phi is acute whenever v is increasing along the curved path. In the case where v is constant, phi is 90 degrees because a parallel is zero. And whenever the case where an object is slowing down as it moves along the curved path, phi, the angle between the total acceleration and the velocity, is less than 90 degrees, and meaning it's greater than 90 degrees, meaning it's obtuse. Obtuse. Greater than 90. Okay. So, very good then. What I can say from this is that when this thing is moving along a curved path like this, at a constant speed, this is the scenario that we're mapping out a circle, and you can see it's moving in a circle. The speed is constant, and therefore it only has one type of acceleration, and that is an acceleration that always points toward the center of the circle. In general motional considerations, we just call that a perpendicular. What I've now told you that also is referred to as the centripetal acceleration. Centripetal acceleration always points toward the center of a circle mapped out by the object. And we refer to that as a special case. That's called uniform circular motion. So bring it back to chapter 2. Because this kind of stuff, this is stuff from chapter 1. So uniform circular motion. Object moves in a circle at constant speed. Moves in a circle at constant speed, and doesn't mean that it's not accelerating. It is, and its acceleration is equal to AC, the centripetal, we'll say. Centripetal. Another version, centripetal. Uniform circular motion, yeah. Well, it has a centripetal acceleration, let's say that. And I'll refer to it as AC or A perpendicular, meaning perpendicular to the velocity. And I guess there is a trigonometric way to derive the formula for centripetal acceleration. It's going to take a little bit more time than I have now. I'm just going to write it down for you. It's kind of a geometric, well, you need a little calculus too in the end. But looking at similar triangles that are mapped out by the object, you know, from a path from the center, looking at similar triangles, and then taking the limit as those triangles go to 0. What you can find, you can do some derivation. In your book, in the chapter, they might spend a couple of paragraphs kind of doing this. They don't do it rigorously, but they might explain it, you know, how you would set up similar triangles to do that. But ultimately, and those of you who've had physics are going to be familiar with this formula. But if you have a circle of radius r and a speed v that the object is moving around, not changing that speed, then what you can see is that the centripetal acceleration, AC, is going to be equal to the speed, the square of the speed over the radius of curvature of the motion. That's a definition of centripetal acceleration. V squared over R. How many people have heard that formula before? By show of hands. No one has heard that before. Okay. All right. All right. Well, yeah, that's centripetal. So usually I derive everything. I wanted to get that down for you so you have it, you know, before the next class period, you can start reading the material. And then a couple other things we can just, once we have that, then, you know, we can just kind of write down a couple other definitions. The period, for example, period of motion is the time it takes to go around one cycle. And one cycle is one complete revolution. Period is the symbol that we use is capital T. And to confuse it from tension, I put little hats on it like this. That's how I write my period, as opposed to just a regular T, which would represent, you know, tension force like I did in a previous problem today. So a period is defined as time of one revolution or one cycle of motion. One revolution or cycle. It turns out something called frequency is the number of cycles per unit time. The processing speed is in frequency, hertz. Its units is 1/seconds, and 1/seconds has a name. It's called a hertz. The time obviously is time, so we already said that. That's units of seconds. Frequency, its symbol is kind of like a, well, at this level, you usually use like a script F. Some people use like a Latin V called nu, but that's more advanced physics. They do that. Here we just say F, and that's defined as the number of cycles per unit time, number of oscillations or cycles. We use cycles right now. Cycles per unit time. And its units are, as I said, 1/2, which is a hertz. And the relationship that frequency has to period is the following. Frequency is equal to the inverse of the period. Sorry, inverse, 1/f. And yeah, so let's box that formula in as a relationship of frequency and period. And as I was saying, the units here, this is going to be 1/seconds. My brackets are in units, and that's a hertz, H-E-R-T-Z, like the car. And it's abbreviated HZ. So hertz abbreviation is capital H Z. And I know it's time to go, but give me 3 more minutes and I can finish this out. So using this formula here and the definition of velocity, we can write the acceleration of velocity a little differently. We can say that in general, velocity is defined as delta V, delta X over delta T. But when you're moving around a circle, delta X is the circumference. And as we just defined, the time to go around one revolution is the period. So the circumference then is equal to 2 pi times the radius over the period. So one way that we can write the linear speed of an object moving around a circular path like this is that V then is equal to either 2 pi r, I'm going to slow those r, divided by the period, or 2 pi r times the frequency, because of the relationship between period and frequency. And so therefore, if I take that velocity and put it into this definition of acceleration, I can write the centripetal acceleration in terms of frequency and period. So if I stick it in, I'm going to have 4 pi squared. And if that's, there's an r in the definition, this would be r squared. So r squared over r squared over r is just r, and then I still have the period there. So that's the centripetal acceleration in terms of radius and period. But if I do it in terms of frequency, then what I have is 4 pi squared. No, sorry. Here. So then this becomes 4 pi squared r times, it's period squared, sorry. So 4 pi r over period squared, or 4 pi r times the frequency squared. Either one of those gives the magnitude of the centripetal acceleration in terms of frequency and period. Now, there's more we're going to say about uniform circular motion, centripetal motion, but we have to wait until we get to Newton's laws, and we'll pick it up again to talk about centripetal force. Right now, we're just kind of focusing on motion, and most books separate out uniform circular motion at this level to kind of start introducing you to these terms. And so, again, I didn't derive that from scratch. Just you have to accept it or look at it in your book, or I might do it as a kind of an addendum to the lecture, because it's really more geometry and trigonometry. I should do it, but it probably takes, to do it comprehensively, it takes about 20 minutes. And then you just get this. So it's kind of feels almost like a letdown. But, And you have now these new, so you have both magnitude and direction of the centrifugal acceleration. I've justified the direction by this argument here that it's always going to be pointing toward the center of the third path. And, you know, that in the case of the special case where the curved path is a circle, it always points toward the center of the circle. To have this in there, it's not a great circle. And these are the magnitudes of the velocity and the acceleration of an object experiencing uniform circular motion in terms of the period and the frequency and the radius, of course. All right, questions, problems, troubles, and or gripes. So that's what I wanted to accomplish today. I was able to do it fairly well within 5 minutes of class. Any concerns or questions or anything? I'm gonna, you know, we got some more examples to be working. I've been working examples probably all day on Tuesdays, on Wednesday, that's what we do. But I'm gonna probably put in an addendum to the lecture too, to give you some more things to think about and some more examples. Now, I want to stress, like a lot of the examples that I do in class, they're kind of similar to, you know, there might be a lot of different parts, kind of like the one I did earlier. You know, that's, you know, with the two, you know, for Coulomb's law. Oh, sorry, what am I talking about? I just had a brain fart. I just switched classes to class this morning. Sorry, scratch that. What am I saying? I just forgot my train of thought. Just a lot of just that I'm using Wiley Plus for the homework problems. That's true. But there are problems in the back of the book that I'm not assigning. Those are the problems that were actually my homework problems when I was going through with this book. And a lot of the examples that I do in class are those types of problems, right? Where there's several parts, you know, like for example, again, brain fart. That was earlier today. But yeah. So I would encourage you to take a look at those problems as well. You know, just for in the process of studying, look at the problems and some of the things, the illustrations or the problem examples I do in class, they'll come from the back of the book or something like it. Those are really good problems to look at. Not the easy things, right? Like the more intermediate problems, where you have to kind of derive things. That's the kind of problems that I do in class as examples. They're comprehensive and more comprehensive than just do some quick little plug and chug type problem. I don't generally do those types of problems in class. But you know, I'll do anything you want if you come to me, you know, if you have like a one-on-one session. But you get more for your buck, you know, if you're trying problems like that, in terms of your growth. All right. Well, any questions before we dismiss class? Well, I appreciate your, yeah, I love you guys coming to class like this. So keep it up and keep working and keep you know, plugging into the modules. I opened week 3 today, and I'm probably going to go ahead and post the exam before the next class period. Don't panic, right? Like it's going to have an opening date, so it won't open probably till next Tuesday or Wednesday, whatever I decide. And you'll have a day or 2 days to do it. But I'm just kind of giving you a heads up. All right. All right. If there are no questions, then class dismissed.
Thank you, Professor. Have a great one.
You just ask. Thank you so much. You just ask Marinelle. You know, you can do it now, or you can send me an email. And I generally try to. I know I've been a little bit. Some of the emails I got a little behind, but the best time is like maybe now in class if you want to set it up and have a discussion. Or you could just, if you don't know what your time schedule is, you can email me, and we can set up through the email through the Canvas. Okay, thank you. All right, have a good day, Akadi. Thank you. Mario.
Thank you, Professor. See you Wednesday.
Okay, see you Wednesday.